Hello everyone, welcome back. So in today's video, we are going to discuss the easiest problem in quantum mechanics, which is that of the free particle. So we are going to look at the Schrodinger equation and its solutions for the free particle. We are going to see what kind of issues these solutions face and how to resolve them, and more or less get an understanding of the quantum mechanical description of a free particle. Now, what is a free particle? It's free. I mean, it is not experiencing any kind of a force in any given system. So in a way, it is experiencing zero potential. So if I take some kind of a point mass particle, which is simply moving about, all right, it's not experiencing any kind of a force. So in that sense, we can say that the potential experienced by the particle is zero. So in that kind of a situation, I want to get a quantum mechanical understanding of this system. So this is a more or less classical visualization of a point mass particle traveling along a particular trajectory. It's a very classical picture. Let us try to understand the quantum mechanical picture. And to do that, first we must write down the time independent Schrodinger equation. So the time independent Schrodinger equation is minus h cross square upon 2m d2 psi upon dx2 plus v psi is equal to E psi. Here psi is a solution of the Schrodinger equation, which is a function of space or x. So let's suppose the point mass particle is only traveling along the x-axis. So it's a 1D problem essentially. V here comes out to be 0. E is the total energy of that particle. Now, if I simplify this differential equation, I simply end up getting minus h cross square upon 2m d2 psi upon dx2 is equal to E psi, which then becomes minus d2 psi upon dx2 is equal to 2m E upon h cross square psi, which finally becomes d2 psi upon dx2 plus 2m E upon h cross square psi is equal to 0. So this is a differential equation, a second order ordinary differential equation corresponding to the free particle, and we are interested in its solution, right? But how would the solution look like? To get an idea about the solution, let's first look at a couple of expressions. So for example, here h cross, you know what h cross is, Planck constant divided by 2 pi. M is the mass of the particle, E is the total energy of the particle. Now, there are a couple of relationships that I want you to keep in mind. So first of all, we have the de Broglie hypothesis, right? Remember de Broglie hypothesis that said that lambda is equal to h upon p. That can be rewritten as p is equal to h cross k. What is k? K is 2 pi upon lambda. H cross is h upon 2 pi. So essentially this comes out to be h upon lambda. All right. So this is the de Broglie hypothesis. Number one. Number two, when we talk about the total energy of the particle is experiencing no force. Therefore, the total energy of the particle is going to be purely kinetic. So E is going to be equal to p square upon 2m. So then this simply becomes p square is equal to 2m E. Alright, so if I want to find out a relationship with k, then what is p square? P square is equal to h cross square, k square is equal to 2me, and therefore k square is equal to 2me upon h cross square. You see this particular expression? K square is equal to 2me upon h cross square. This is nothing but the constant here, 2me upon h cross square. So I can rewrite the differential equation in a slightly different manner. So let me just rub this for the time being. This differential equation can be rewritten as d2 psi upon dx2 plus k square psi is equal to 0. Now you do realize what k here is, right? K is nothing but the wave number, all right? And it is related to the momentum and therefore related to the total energy of the particle. So what is the solution for this kind of a second order ordinary differential equation. If you are familiar with differential equations, then equations of this form have a very standard general solution, which is what I'm going to write here. It is written as psi x is equal to, let's suppose, some constant a, e to the power iota k x, with respect to which the derivative is, plus b e to the power minus iota kx. Now this is the solution of the Schrodinger equation, which is time independent. Therefore this is basically dependent upon only x. Now if I want to write down the complete wave function solution, for that I will have to include the time dependent part. So in that situation, the wave function, how do I write the wave function? I multiply the eigenfunction with e to the power minus omega t. Remember, when we use the separation of variables method, when we obtain the time independent Schrodinger equation from the time dependent Schrodinger equation, we found out that the time dependent part had the expression of e to the power minus omega t, which I'm going to multiply to this to get the wave function, which is a function of x and time. So thereby we get a e to the power iota kx minus, the time dependent part is iota omega t. So this is going to be kx minus omega t and plus b e to the power, here I have minus iota kx, again minus minus becomes plus omega t. So this is your wave function solution for a free particle. Now what does this function actually represent? That is a good question. What does this function actually represent? You see, this is nothing but a plane wave solution. It's a plane wave solution. Plane wave means it's a very simple sinusoidal variation. It's not complicated at all. Now, the first part here simply refers to a plane wave solution which is moving forward, and the second part refers to a plane wave solution which is moving backward. So this is essentially a, I can say, forward moving plane wave Now this part refers to a backward moving plane wave. You see, when we talk about a free particle in quantum mechanics, then the Schrodinger equation gives us a plane wave solution moving both forward and backward in space, which is what the quantum mechanical description of a point mass particle moving in the absence of any kind of a potential is. Now, what can we deduce from here? The first thing is that this forward moving wave and the backward moving wave are associated with a forward moving particle, right? So a forward moving particle and a backward moving particle respectively having fixed momenta and fixed energy. All right. So what is the fixed momenta? The momenta is P equals h cross k, but for the forward moving particle it is plus h cross k, and for the backward moving particle it should be minus h cross k. And similarly, the energy of the particle is p square upon 2m. If I substitute h cross k here, I should get h cross square k square upon 2m. So h cross square k square upon 2m, again basically for the particle moving forward and backward. Now there is an issue with this. I mean, the first thing that you'd probably notice is that the momentum has a fixed value, the energy has a fixed value. Is it possible? I'll come to that in a moment. Okay, so there are a couple of issues with this plane wave solution for a free particle, and I'm going to describe you three main issues that we see here. The first issue is that if I try to figure out the probability density associated with this Schrodinger, wave solution, then if I try to measure the probability for, let's suppose, the forward moving wave, I'm going to call this as psi plus, and the backward moving wave, I'm going to call this psi minus. So let's suppose I choose psi plus or psi minus mod square. Now what is this? This is nothing but you end up getting a star let's suppose I choose the forward moving wave, I end up getting e to the power minus iota kx minus omega t, and then you have a e to the power iota kx minus omega t, right? I take the complex conjugate, but clearly this and this gets cancelled, so you are left with a star a, so a mod square. Now here a mod square is basically a constant. It's a constant that we can find out by giving some sort of an initial condition to this particular differential equation. So if I write down the nature of the probability with respect to x, if I look at the probability density, okay, psi square, it comes out to be a constant line. How is that possible? The particle is moving, right? The particle, at least it's supposed to be moving from one point to another. Then the probability associated with the plane wave solution corresponding to that moving particle is constant from minus infinity to plus infinity. That's interesting. One of the reasons for this could be that we have a fixed momentum. Now you already know in Heisenberg uncertainty relation, we can never really accurately measure the momentum and the position of a particle with absolute accuracy simultaneously, right? But here I am getting a definite value of momentum for this particular forward moving plane wave, which means that the uncertainty associated with the position tends to infinity, which is what's happening here. We have no information about the particle's spread in terms of its position, right? Similarly, because the energy is fixed, we have no information in terms of the change in the particle's probability density with respect to time. So even del t tends to 0. This happens because del p is equal to 0 and del e is equal to 0, right? Two things that are not allowed by the uncertainty principle. But because we have fixed values of momentum and fixed values of energy for a given plane wave solution, del x and del t both become infinite, and therefore we have no information about their spread. Therefore the probability density is a constant. That's a problem. That's a problem, right? But before we solve that problem, let's go to point number 2. When we try to measure the velocity of this plane wave solution, then we find something again interesting. So what is the velocity of this plane wave solution? The velocity of a wave is mu times lambda, right? Mu can be written as 2 pi nu and lambda upon 2 pi. So this is omega and this is k, omega upon k, right? Now what is omega? Omega is nothing but E upon h cross. So we know that E is equal to h cross omega, Planck postulate. So omega is equal to E upon h cross. So this is equal to E upon h cross k. But what is E? E is equal to p square upon 2m. P is again h cross k. So h cross square k square upon h cross k times 2m. So therefore here h cross k gets cancelled and we are left with h cross k upon 2m. Perfectly fine. This is supposed to be the velocity of this particular plane wave. Now, if we compare this with the velocity of the particle, what should be the velocity of the particle? For the particle, the velocity is equal to momentum divided by mass, right? The velocity of a particle is momentum divided by mass. Now again, P is equal to h cross k. So this is equal to h cross k upon m. If you make a comparison, h cross k upon 2m and h cross k upon m. So this is the velocity of the wave. This is the velocity of the particle. How do I separate it? So essentially, the velocity of the wave is half times the velocity of the particle. Now, what does this actually mean? Does it even make any sense? It doesn't. So clearly there is some issue here. Another one important aspect I want to reveal is related to normalization of this plane wave solution. Now in the third point, if you try to normalize any one of these, either forward moving or backward moving plane waves, then you will find that if you calculate the probability, let's suppose of psi plus minus, and with respect to x between minus infinity to plus infinity, you can clearly see that this, of course, the iota, this will get cancelled. So essentially you end up getting a mod square integration from minus infinity to plus infinity dx. Can you see that? This term and its complex conjugate will cancel out. So all that is left is a mod square. Now what is this integration of dx from minus infinity to plus infinity? This tends towards infinity. How is it possible that a probability of a particle being found between minus infinity to plus infinity is not equal to 1? Then it doesn't really make any sense, because then this wave function solution is not physically realizable in the sense that it does not represent a physical particle. So clearly you can see that we can't use this solution of the Schrodinger equation for a free particle, because we have certain restrictions on the solutions of a Schrodinger equation that it must satisfy for it to be actually applicable for a physical system. And one of those restrictions is that it must be normalizable. It is not. This is what we get from the Born statistical interpretation, that the probability of the particle being found from minus infinity to plus infinity should always come out to be equal to 1, because that's what it should be, because that's what it is. But because the wave function itself does not give us that information, that means there is something wrong with it. So you can clearly see that even though the Schrodinger equation gives us plane wave solutions, it gives us constant probability, doesn't really make much sense. It gives us velocity expressions, which is not the, the velocity of the particle is not the same as the velocity of the wave, and the function is not normalizable. So what do we do now? We are in a little bit of a problem. What can we do about it? See, the thing is, for a free particle, the plane wave solution does not represent the particle. So what we can do is, we can use the concept of a wave packet. So we can take the plane waves, and there are a large number of plane wave solutions, and we can perform a linear superposition of the plane wave so that we end up getting a wave packet. So this is known as the concept of a wave packet, where we take a large number of the plane wave solutions of the Schrodinger equation, and then we take a linear superposition of them, we add them up so that they all constructively interfere in a very tiny region in which the particle exists, so that we get a non-zero amplitude, and beyond that, away from that region, they destructively interfere, so therefore the wave packet vanishes. So essentially it is a localized wave packet in a region in which the particle exists, which can be constructed by a linear superposition of a large number of plane wave solutions. So this technique of creating this wave packet will sort out all these issues. So I have already talked about this concept of wave packet in a couple of my videos, where I've gone in detail into the nitty-gritties of what is a wave packet and the various physical parameters associated with it. But I'll just concisely say here that for a free particle, we can't really wave the plane wave solution, but we can use a linear superposition of a large number of plane wave solutions that results in a wave packet. How do you construct a wave packet? So let's suppose a particle is moving in the forward direction. I take, let's suppose I have A. I modulate, of course, A with respect to some sort of a relationship with wave number, e to the power iota, e to the power iota, kx minus omega t, integrate with respect to dx between, not dx, sorry, with respect to k, and then normalize it properly to get this wave function corresponding to the wave packet. The wave packet concept kind of avoids these issues. Number one, because the wave packet is localized in a very specific tiny region, and its amplitude is non-zero in a very tiny region. That means if I try to find a probability density associated with a wave packet, we will see that the probability density is higher in the region in which the particle actually exists and lower away from that particular region, number one. Number two, because the wave packet is constructed by a large number of plane wave solutions which are differing from one another in terms of its k, so essentially we end up creating a situation in which there is a distribution of the wave packet in position space and the distribution of the wave packet in k space or momentum space, and both are inversely correlated to one another. There is no definite momentum or definite energy associated with the free particle. In fact, there is a spread in the position as well as the momentum associated with this kind of a wave packet distribution, which essentially corroborates the Heisenberg uncertainty relationship, and therefore we avoid this kind of a scenario. Also, when we calculate the velocity of a wave packet, if you have seen my earlier videos on wave packets, you would know that the velocity of a wave packet essentially comes from something called group velocity. So how do we calculate group velocity? Group velocity is calculated as Vg is equal to d omega upon dk. Alright, so if I do d omega upon dk, what is omega? Again, omega is equal to E upon h cross. H cross is, so basically E is equal to h cross square k square upon 2m. So this comes out to be d upon dk of h cross square k square upon 2m, but because omega is equal to E upon h cross, so I should get this. So if I do a derivative with respect to this, k, 2 will get cancelled. I will end up getting h cross k upon m. What is h cross k? H cross k is momentum. Momentum upon m is simply equal to the velocity of the particle, right? Velocity of the particle. So in this kind of a scenario, the group velocity of the wave packet is exactly equal to the velocity of the particle. So you have solved that issue also. And again, the wave packet can be normalized. We can normalize it to make sure that the probability of the particle being found in the entire region comes out to be 1. So by introducing the concept of a wave packet as a linear superposition of an infinitely large number of plane wave solutions of the Schrodinger equation, we avoid these issues and then come up with a realistic model for a free particle. So for a free particle, whenever a particle is moving in a force-free space, we can represent a wave packet that evolves and moves at a particular speed, thereby giving us a representation of the quantum mechanical version of this free particle system. So that is all for today. I think you have got some understanding of free particle and the issues regarding the plane wave solutions and how we can resolve them by introducing the concept of the wave packet. Again, I have discussed a lot about wave packet in some of my earlier videos. If you want a little bit more depth into this topic, you can watch those particular videos. But for today, this is enough. Thank you so much. Take care. Bye-bye.